Welcome back. We are talking about the TCP window scaling option. Window size can be increased because the satellite link has a large RTT. This was the last slide we have seen. There is a provision for the window scaling option that is to be activated in case of satellite link, that is a large RTT link. Let us take an example and try to see how it is. Estimate TCP throughput with RTT of 0.1 second and TCP window size of 2^16 bytes, that is 65,535 bytes. Now, the initial throughput is window size divided by RTT, which is 655,350 because 0.1 in the denominator, so many bytes per second. That is the initial throughput. Now, if a satellite link is introduced in the signal path, RTT increases by another 0.5 second. So, it will become 0.1 plus 0.5, 0.6 second. Can the same throughput be maintained? No. New throughput will be W by new window size. Since the RTT has increased, it will decrease. So, initial value was 655,350 bytes per second. Now, it will be 109,225 bytes per second. This is lower than the initial throughput. So, what is to be done? To maintain the earlier throughput, window needs to be scaled up by how many bits? Okay, let us calculate that. New window size will be throughput into new RTT, and which is throughput was 655,350 and new RTT is total 0.6 now. So, the window size will be 393210 bytes. So, this is in 2 to the power how many bits represent this? 2 to the power 19 is 524288 and 2 to the power 18 is 262144. 2 to the power 18 will be smaller than this. So, 19 bits are required. So, 19 bits are required, and normally the window is 16 bits. So, 3 more bits are required. So, window scaling has to be by 3 more bits. So, this is how we quickly calculate. Okay. Now, let us go to the another important issue, which is called flow control, which is very important. Flow control is needed to maximize the capacity utilization. Now, both transmitter and receiver can control the traffic. Transmitter and receiver both can control this traffic flow. Receiver side flow control is receive buffer to avoid overflowing the receive buffer. Receive buffer, if it is full, it is not yet read properly, and then another data has come, it will overflow. So, receiver has to stop that, and this is set by the receiver. So, that flow control is set by receiver, and this is set by a parameter which is called RWND, RWND receiver window, which is a receiver advertised window. Receiver at the beginning of the connection, it says this is my RWND, and of course, he can control by ACK, he can hold the ACK, he can delay the ACK. So, the ACK is another thing which is the clock of the total system. So, with RWND advertisement as well as by ACK, he can control the flow of the input traffic. And the transmitter side flow control, let us see. It avoids the overloading the network. The network capacity it has to understand, but it is transmitter, how it will understand? So, it will go slowly. So, it is set by the sender, the transmitter will be setting, and it estimates conservatively to avoid network overflow, capacity overflow. That is increase traffic slowly, which is named as a slow start, and then avoid congestion, avoid network congestion, which is called congestion avoidance. 2 different phases it will go. It goes slowly and then tries to avoid the congestion. For that, he sets 2 parameters, which is CWND, which is congestion window, and slow start threshold, SS threshold. There is a threshold value, and congestion window will be variable on that. Threshold value also will change depending on the situation. So, initially it will be setting the window is equal to minimum of CWND and RWND, that is receiver cannot accept beyond that. So, RWND and CWND will be varying. Let us see. Slow start phase is defined as when CWND is less than threshold, slow start threshold. So, it starts with 1 times MSS, that is maximum segment size. Now, I am showing the initial days of internet. Nowadays, they have done a lot of research, and this has become 2 into MSS, but let us not go into too much of details of that. It is just a philosophy we are discussing. So, start of the it is easier to understand also. Start with CWND 1 into MSS, then for each of the ACK of this MSS or the sequence, the CWND will be increased by CWND whatever earlier was there plus 1 MSS, and CWND obviously grows exponentially. Let us try to understand with this picture. Transmitter send a data packet, one segment, and the acknowledgement for the segment has come. So, it will increase by 1 MSS. So, you can window has increased, CWND has increased from 1 plus 1 acknowledgement has come. So, it will send 2 of them, 2 segments. So, for 2 acknowledgement comes. So, for each acknowledgement each increases by 1. So, for 2 it will increase by total 2. So, earlier 2 plus 2 makes it 4. The 4 acknowledgement comes, it will make it 4 plus 4 8. For each acknowledgement it will increase by 1, and earlier more than earlier one, CWND plus MSS. So, therefore, it is going by 2 to the power exponential growth. And in the congestion avoidance, when the CWND is greater than SS threshold, then it will, for any group of acknowledgement, it increases by only 1 MSS. So, it grows linearly. Pictorially, the data packet is sent, acknowledgement has come. Let us assume the CWND is in that situation. So, for acknowledgement 1 increases. So, now 2 data packets have been sent. So, when 2 are comes, this is a group. In this group, he increases by 1. So, it makes it 3. When 3 comes in a group, then it increases by 1. So, makes it 4, like that. So, it can be plotted like this, that this x axis is RTT and CWND in terms of MSS. So, there is a SS threshold set, and CWND increases slowly, but then exponentially quickly, and once it reaches SS threshold, it goes linearly. So, this is the slow start phase, and this is the congestion avoidance phase. Okay. So, slow start phase is CWND is lower than SS threshold, and congestion avoidance phase is CWND is higher than SS threshold, that you have to remember. Okay. So, during slow start, CWND increases by 2 to the power n. So, n is the number of grouped transmission. So, time to reach this SS threshold, if we say this will be my throughput. So, time to reach that is n times RTT is 2 to the power n, and n times how many RTTs it is passed. So, n times RTT. Given the segment size, RTT and SS threshold, derive an expression to find duration of slow start phase. Number of RTT to reach SS threshold is n, and as CWND increases logarithmically in slow start phase, 2 to the power n is equal to SS threshold by segment size. So, duration of slow start phase is n into the RTT. Okay. Given segment size, RTT and SS threshold and the latest CWND, derive an expression to find duration of in the congestion avoidance phase. So, when it is growing linearly, that is CWND is more than SS threshold. Number of RTT to reach from SS threshold to the latest CWND, let us call it m. So, as CWND increases linearly by 1 segment in congestion avoidance phase, so m is latest CWND, which is higher than SS threshold minus SS threshold. So, how much higher, divided by the segment size. So, I got m. So, m times RTT, that is the duration in the congestion avoidance phase. So, it goes like that. So, it grows x axis is RTT, y axis is MSS. So, it grows like this exponentially, and let us see at a time, let us say acknowledgement not received, then that means RTO fired. Once the RTO fires, TCP flow control, center flow control says that some congestion has occurred. So, you start from the beginning, you drop and start sending only 1 byte, 1 segment, and since and SS threshold whatever was there is also reduced. So, it goes slowly, and once it reaches SS threshold, it goes. So, SS threshold level is also reduced by half. RTO for a packet expires assumed network congestion. So, SS threshold is reduced by CWND by 2, whatever CWND was there. CWND is reduced to 1, in actual case today's scenario it is 2, and RTO is doubled. These details, let us not go into details of that. When a packet is not received within the expected time, in a error free network, segment loss indicates a congestion, that is the TCP protocol, but segment loss is detected by retransmission timeout or duplicate ACK. We have seen earlier the duplicate ACK says that there is segment loss, but subsequent segment has gone. So, expected next byte in the sequence, which says like that in the buffer segment 1, 2, 3, 4 has not been received. So, there is a hole. So, you will send the acknowledgement for 3, 3, 3 like that, all subsequent segment when it is received. Now, there is a protocol, if RTT, you do not wait till RTT, a segment is lost, 3 acknowledgement has been received, duplicate acts. So, we can call it a fast recovery. So, since each duplicate act indicates that segment is successfully received and left the network, so you can fill up the network, immediately retransmit the lost segment after the 3 duplicate acts without waiting for its timeout. If it is timeout, then you have to go down to almost 0, that is 1 segment you have to start. And then when 3 duplicate act received, SS threshold is reduced to half, that is the fast recovery phase, and CWND, new CWND will be CWND by 2, and since 3 segments have been sent, so it will be increased by 3, so slightly inflating that. So, this is the quick recovery of the system without going down to slow start. And then there is something called fast retransmit. When sender retransmits the segment for which duplicate ACK is received, this continues till subsequent duplicate ACK is being received and RTO has not expired. For each duplicate ACK, one segment can be sent. If the RTO expires, SS threshold will be reduced to CWND by 2, CWND will be reduced to 1 segment, and slow start begins. That is a usual RTO procedure. And if RTO fire has not occurred and the new acknowledgement is new segment is acknowledged, all previously received segment, then you continue for the last segment sending. Then CWND is set equal to SS threshold, and congestion aversion phase starts at half the throughput. There was a loss, so which may indicate a congestion. So, you reduce the throughput, and when the loss was detected, and through duplicate ACK. So, this is called fast retransmit without going to slow start phase. Halfway through it starts. Now, we will use some example to understand with certain numbers. Let us assume RTT is 0.5 second, which is satellite delay. SS threshold is 64 kilobyte, and segment size is half kilobyte. Find slow start duration without a loss of any segment. Slow start duration will be RTT into log base 2 SS threshold by segment size. We have seen this earlier. So, this is 0.5, that is RTT is 0.5 second multiplied by log of 64k by 0.5k, which is 3.5 seconds. That is the slow start duration to reach the SS threshold level. Find how many bytes are in flight at the end of slow start phase. Window size, the number of window size is the number of bytes in the flight. So, since we are reaching the SS threshold level, so at the end of the slow start phase, it is 64 kilobyte, which is already specified SS threshold. Therefore, 64 kilobyte are in the flight at the end of slow start phase. And find the maximum throughput at the end of slow start phase, that is at when it reaches the SS threshold. So, maximum throughput is the maximum CWND by RTT, SS threshold by RTT, which is 64 kilobyte by 0.5 second, which is 125 kilobytes per second. After that, congestion aversion phase starts. So, let us do some calculation on that. Before that, okay, if RTO fires after CWND has reached SS threshold, that is 64 kilobyte, what will be the values of new SS threshold and CWND, and which phase it is, how long it will take to reach the throughput of 128 kilobyte per second again. So, after RTO fires, SS threshold will be sent CWND by 2, and CWND will be sent to 1 segment, which is SS threshold will be half of 64 kilobyte, which is 32 kilobyte, and CWND is 0.5 kilobyte. It is now in the slow start phase because CWND is lower than new SS threshold. So, duration of this phase will be again 0.5 log 2. Now, it is 32 kilobytes. So, 32 by 0.5 that is equal to 3 seconds. This time it will be 3 seconds. Then the congestion aversion phase starts. So, the number of RTT in this phase to reach the CWND 64 kilobyte from 32 kilobyte in increment of 0.5 kilobyte each is, it is a linear growth. So, 64k minus 32k divided by 0.5k is 32 by 0.5 is 64 steps are required. So, duration of SEA phase is RTT into 64, RTT is 0.5. So, it becomes 32 seconds. Linearly it is going very slowly. So, total duration is 3 seconds to plus 32 seconds, that is 35 seconds. So, you see with the example of the RTT is equal to 0.5, these two phases, RTO firing and what happens, all these things we have seen, and you see how slowly it is going. the maximum throughput, that is the network capacity, what it can support, how slowly we are trying to we are reaching to that maximum capacity. Now, if 3 duplicate acts received when the CWND reaches 64 kilobyte, followed up by up to date act reception when the missing segment is transmitted, what phase it is and how long it will take to reach the maximum throughput of 128 kilobyte per second again. This is a fast retransmit and fast recovery phase. So, after 3 duplicate act received, fast retransmit and fast recovery phase starts. Now, SS threshold is CWND by 2 as per fast recovery and fast retransmit, and CWND will be SS threshold plus 3 segment, because 3 duplicate act received. So, 3 segment is increased, and congestion avoidance starts. Congestion avoidance starts because CWND is more than SS threshold. It is new SS threshold plus 3 segment. Since it is more, so therefore, it is a congestion avoidance phase. So, new SS threshold value is 64 kilobyte by 2 is 32 kilobyte, and new CWND value is 32 kilobyte plus 3 times 0.5 kilobyte, that is 33.5 kilobytes. And the duration to get up to date ACK is 0.5 second. Then the fast recovery phase sets the CWND is equal to SS threshold 32 kilobyte, and congestion avoidance phase starts. Now, because CWND is more than SS threshold, duration of this phase to reach the maximum throughput, which is 64 kilobyte is 64k minus 32k divided by k is missing here, 32k divided by 0.5 into RTT. So, that makes it 32 second, just like our earlier example, it takes that much time. So, the total duration is 32.5 seconds. So, in this process of our with some simple type of example, what we are seeing is that if there is a packet loss either by RTO firing or by duplicate act received, whichever way you go, because RTTs are large and window is maintained at 64 kilobyte, you are reaching of the order of more than 30 seconds. You are reaching the maximum network capacity or maximum throughput. It takes quite a long time. So, this is one of the major issue that people have faced when they come into this long delay fat network, where the packet drop may not be, that is very important, the packet drop may not be due to congestion. In the normal TCP protocol, it is assumed that it is due to congestion. Any packet drop is due to congestion, it is not because of the error. So, therefore, the space communication transport protocol, which is slightly modification of the standard TCP for the space related use, has been proposed. Now, space communication environment differs significantly with terrestrial environment. That aspect, that is the effect that transport protocol has to take. So, transport protocol performance will be different, not the expected. So, the primary difference is, there are many differences. The primary difference is the what is the source of data loss, because we have seen the satellite link is a error prone link, and we have seen that it is intermittent connection. We have also seen that a network capacity is limited. So, because of that, there may be certain data losses which may not be always congestion. There will be congestion also, there is possibility of congestion. So, in terrestrial, any loss is due to congestion, it is assumed that it is due to congestion, whereas in space it is a corruption due to noise or link outage or congestion, either due to noise or the link outage or the congestion, or any one of the three are possible. Because of it is because of noise and link outage, it should not be treated as a congestion, and you should slow down the flow drastically. So, approach to the loss recovery must be different. That is the one of the major issue in the modification of the TCP protocol in the space environment. So, space communication protocol is a standard for communication protocol standard for transport protocol. The name is SCP/STP. That was developed and accepted by standard body like CCSDS, which stands for Consultative Committee for Space Data System. This like ITU, International Telecommunication Union, which we discussed earlier, they specify the physical layer, that's the satellite to earth, earth to satellite, the link, what should be the parameter, where the satellite can be placed, what should be the frequencies. So, similarly, for the space data system, ITU talks about not only space, it talks about other systems also, terrestrial as well as meteorological and many other systems. In only for space, there is a consultative committee for space data system. They specify this, that is the standard body. Most of the space agencies, all the space agencies, they follow this standard. So, they have developed or they have studied and modified the TCP protocol accordingly. So, it is called SCP/STP. We will briefly touch upon the SCP/STP, what are the modifications that is done in TCP and why and how. So, standard TCP assumes the packet loss due to congestion only, and to reduce the network congestion, throughput is reduced. That's what we have seen, that is drastically reduced and goes into slow start phase. Or even in fast retransmit, fast recovery, the network throughput is reduced to half. In uncongested network, that harms the performance. So, in satellite network, packet loss could be due to noise or due to corruption of a segment. I mean, noise is a corruption of the segment. This is the thermal noise what we are talking, and it could be the link outage, as we have discussed, that the satellite may go behind under the shadow of another object. It could be another planet, or it could be link outage due to other phenomena in the propagation phenomena like heavy rain or solar flare, etc. And it could be also due to congestion. That is also another possibility. Now, in the satellite link, the source of packet loss needs to be identified. Like here in the case of terrestrial link, the source of the error is always assumed to be congestion. Here, out of these three, whether it is congestion, link outage or corruption, that has to be identified. So, the accordingly throughput reduction can be avoided in the uncongested cases. This is the major thing how it is done, it is error prone link. So, now we will discuss in the each of the three cases that how these four phases which are used for corruption. That is, for first is the onset of the corruption has to be recognized. Now, how it can be recognized? At the TCP level, we have seen the sender looks only at the receiver advertised window, or it tries to see when the acknowledgement is coming, or acknowledgement duplicate acts are coming or not. From that, in case of space link, that corruption upset can be found out that from the link layer. The link layer has a protocol which detects the error. That is, there is a CRC. In case of TDMA, we have seen that CR, BTR, Unicode missing, the probability of miss of Unicode, and also there are other protection error checksums are there. So, link layer somehow knows that there is a error which is occurred. Link layer can find out. So, the corruption started, that is noise has occurred, link layer finds out. So, if this information is passed on to the higher layer, then higher layer can take as an understanding that that it is not a congestion, it is corruption. That is what is happening. So, link layer pass on this information about the loss, that is the packet has a CRC error. CRC is cyclic redundancy check, CRC error, but can be demultiplexed. Receiver runs the moving average of such packets and compares with a preset threshold. So receiver doesn't take an immediate decision, it just goes on checking how much noise is increasing. So it goes on accumulating that this information of CRC error which is coming, how much over a period of time. So it runs a moving average, and of course it checks with a threshold. So if it's a very sparse phenomena, then it ignores, it knows that there is a error, but if it is exceeding certain threshold, it alerts that there is a corruption onset is happening. Anyway, the time is almost up, so we'll continue the discussion in the next session.